Welcome back to The Explainer. Today, we're diving deep and equipping you with an advanced quantitative toolkit for electric motor systems. This is all about moving past the basic efficiency ratings and into a really rigorous, data-driven approach that ties engineering decisions directly to financial outcomes. Okay, let's start with a number that should honestly stop everyone in their tracks. We all know it, but have we really absorbed it? Energy can make up to 96% of a motor's total life cycle cost. When you see it like that, the initial purchase price is, well, it's practically a rounding error. This single fact completely changes the game. It means we have to stop treating motors like simple components and start managing them like long-term financial assets. So here's our roadmap for today. We're going to start with that big financial why, the 96% imperative. Then we'll get into the nitty-gritty and decode the core performance equations. After that, we'll apply them to diagnose some real-world losses, look at the incredible power of speed control, and wrap it all up with a framework for strategic, portfolio-level motor management. Right, so that 96% figure isn't just a fun fact. It forces a massive shift in our mindset. We're not just managing pieces of equipment anymore. We're managing a major financial portfolio where the operational data, the numbers, are the main lever we have to pull for performance. And just to be clear, this isn't some niche problem that affects a few machines over in the corner. We're talking about the biggest single energy user in most industrial plants. I mean, globally, electric motors are the largest end use of electricity, period. The sheer scale of it makes motor optimization a top-tier strategic priority for any serious energy program. Okay, now for the core of our toolkit. Let's be very clear. We are not treating these equations like some academic exercise. These are your diagnostic instruments. Mastering this language, and it is a language, lets you quantify performance, pinpoint waste, and, maybe most importantly, build an absolutely rock-solid business case for any improvements you want to make. First up is real power, measured in kilowatts. This is the working power. It's what actually spins the shaft, and it's what you get billed for by the utility. For our purposes, the most important thing here is getting an accurate field measurement, because this number is the baseline for every single calculation that follows. If your kilowatt reading is off, the whole analysis is junk. Now, the distinction here is absolutely critical out in the field. See that square root of 3, that 1.732 factor in the three-phase formula? That's there to account for the phase displacement in the sine waves. And believe me, a really common mistake during quick assessments is to use this single-phase formula on a three-phase motor. You do that, and your power calculation will be off by over 42%, completely invalidating any conclusions you draw. Next up, power factor. Think of this as your key indicator of electrical efficiency. A low power factor isn't just about risking penalties from the utility. It means you have wasted capacity in your own infrastructure. That excess reactive current doesn't do any work. It just creates thermal losses in your transformers and your wiring, holding your whole electrical system back. And this is why it's a systemic issue. The absolute workhorse of industry, the AC induction motor, is fundamentally an inductor. That's just its nature. So you get this inherent lag between the voltage and the current that we constantly have to diagnose and manage, especially on motors that are lightly loaded, because that's where power factor really tanks. And finally, of course, motor efficiency itself, or ADA. It's the simple, almost brutal ratio of mechanical power you get out versus the electrical power you put in. Every single percentage point of loss here turns directly into waste heat. And that doesn't just impact your energy bill, it shortens the motor's life and hurts its reliability. All right, let's move out of the textbook and into the real world. Let's see how these equations become really powerful diagnostic tools. We're going to apply them now to diagnose some of those costly and often hidden operational problems that, let's be honest, plague motor systems in just about every facility out there. So here's a critical question. How bad can a little voltage imbalance really be? I ask because this is a true silent killer of motors. It's an incredibly common power quality issue, but it gets underestimated or even ignored all the time, leading to early failures and a ton of wasted energy. Now, the thing you have to burn into your brain here is the exponential relationship. The damage increases with the square of the imbalance. It's not linear. Why? Because those imbalanced voltages create a negative sequence, basically a magnetic field that's trying to spin the motor backward. This induces these high-frequency currents in the rotor, leading to incredibly rapid and totally disproportionate heating. So let's put some numbers to that. Say you have a seemingly tiny 3% voltage imbalance. Well, you square that 3% and you get 9. Then the formula doubles it. The result is a staggering 18% increase in resistive heat losses in the windings. This is not a theoretical number. This is real heat that is literally cooking the motor's insulation from the inside out, leading directly to premature failure. Okay, so we've diagnosed the problem. Now let's shift to intervention. We're going to focus on what is arguably the single most powerful lever we have for optimizing motor systems, especially when they're driving centrifugal loads like fans and pumps. And that is, of course, variable speed control. The Affinity Laws. This is the physics that makes VSDs so effective. But remember, this is specifically for centrifugal loads. Look at the compounding effect here. Flow is linear with speed. Fine. Pressure goes up with the square of the speed. But here's the money shot. Power draw is proportional to the cube of the speed. That cubic relationship is the key that unlocks absolutely massive energy savings. And here is that third law in living color. A modest 20% reduction in speed doesn't get you a 20% savings. No way. It results in a power draw of just 51.2%. That's a nearly 49% energy saving. Now compare that to just closing a damper or throttling a valve, which just burns off all that excess energy as useless heat and pressure. That is the fundamental difference. Okay, let's zoom out now. We've been talking about individual tactics, but to really capture these savings at scale, we need to elevate this to a comprehensive, long-term strategy. You've got to think beyond just one motor and start managing your entire portfolio with a structured, data-driven approach. The classic dilemma, rewind or replace. And while a rewind looks cheaper on the initial invoice, if you run a full life cycle cost analysis, which we now know is dominated by energy, replacement almost always wins. And it's not just about the guaranteed high efficiency of a new motor. It's also about avoiding the efficiency loss, often 1 or 2 percentage points, that can happen during a rewind if it's not done to very strict specifications. And this is how we move from reactive tactics to proactive strategy. You build a motor performance management process, an MPMP. It's about making all these best practices routine. You identify your critical assets based on run hours. You use standardized software for unbiased analysis. You make life cycle costing the default for every repair-replace decision. And you build things like power quality checks right into your regular maintenance schedules. It's a total game changer. And look, if you need one final data point to make the business case, this is it. The annual cost to run a motor can easily be 5, even 10 times what you paid for it. This just perfectly sums it all up. The purchase price is trivial. Our focus, our rigor, has to be on managing that operational cost, because that is where all the financial leverage is. So we'll end with this question for you. Now that you have this toolkit, which motor out on your floor represents the biggest hidden liability? Or, looked at another way, your single greatest opportunity? The truth is, your next big energy project isn't waiting for some brand new technology. It's probably just sitting there, waiting to be diagnosed with the tools you have right now.